Welcome to this video series where we look at the SimpleCPU game console, so how it was developed, its background, and perhaps more importantly, how to program it so that you can use this platform to write your own games. To state the obvious, if you're building a games console, you need three main things. You need a controller so the user can interact with the game, you need a processor to process those signals, process the game logic, generate the graphics, and then send that to the display so the user can see it. So these are the three things that we need to design, and that's what we're going to look at in this video. So we're going to give an overview of these three main building blocks. So that was always the intention for the SimpleCPU processor. The basic idea was that students could build their own processor and then use that to build a simple games console, something you could play simple games on. So just to be clear before we get started, we're not looking at any HD first-person shooter-up type of system. We're looking for basic retro games, such as you can see here. So top left we've got Combat, so kind of a tank game based around a maze. Top right I think is it Warlords? So that's kind of a mix of Pong and Breakout. It was a 4-player game, I believe. Bottom left we have a Space Invaders clone. Yeah, maybe not as good as the arcade one, but you can see what they're going for. And the bottom right, I think that was Berserk. We had to speed run through a world shooting robots, if I remember correctly. And obviously in the same sort of graphical style that we have Pac-Man, Snake, all those sort of games where you've got very simple blocky graphics, relatively small programs that could be implemented by a small 8-bit or 16-bit machine. Okay, so the first thing I considered when building this console was the display. Obviously nowadays HDMI is the go-to video standard, but that's too complex really to implement on our simple system. We don't have enough processing power or memory to implement that. Also, the aim was that the students could pick up a cheap FPGA board to build this system on. So again, to implement HDMI, you'd need a bigger FPGA, and that all adds to the cost. So we're looking to implement an Atari 2600 style of game console, as you can see in this picture here. So to start off with, I did consider perhaps you could make this a handheld console, so an LCD or some sort of LED display, which would greatly simplify the hardware interface needed on the FPGA, as the communication link between the processor and these types of displays is typically either GPIO, I2C or SPI interfaces, which are quite easy to implement in the FPGA. But I decided not to go that route. As you're tying the console down to a specific piece of hardware here, I wanted to keep it more general. Therefore, if you rule out LCD displays, HDMI, DVI, those sort of interfaces, that's really pushing you into one direction, VGA. And from one point of view, that may seem problematic because obviously VGA uses analog signals to represent the red, green and blue color components. But when you look at a simple VGA interface that can be implemented using a resistor ladder to implement that DAC functionality. So what you effectively have is a potential divider. So each color input on the VGA connector is terminated with a 75 ohm resistor, and combined with resistors you can see in this diagram, that forms a potential divider. So if you look on this web page here, I implemented a simple SPICE simulation of such a network. So you can model the digital outputs as voltage sources, outputting a 0 or 3 volts. And going through the different binary combinations, you can change the analog output to the Vout in this example here, as shown by this graph. So connecting to the VGA display is relatively simple and low cost, which both are positive selling points for this cheap games console. Once I had decided upon using VGA, then thoughts turned to building the video controller in hardware. And typically that will mean having a frame buffer, somewhere where you can store the pixel data, the pixel values that you'll be using to drive that VGA display. Obviously I would like a nice big display, but that's a problem because the FPGA has limited memory. You can buy FPGA boards that have external memory, typically a DRAM attached to them. But again, that adds cost to the FPGA board, and also you need to use up some of your FPGA's resources to build a SDRAM controller to allow the processor to interface to this external memory. A far simpler solution is to use the FPGA's on-chip memory to make a system-on-a-chip design to have a single IC-based solution. And that's what I wanted to go for this games console. I wanted everything to be on a single FPGA. Now that obviously means we have to start to think about how big a resolution our games controller can have, as you can see from this table. If you have 800 by 600 pixels, going for the maximum color resolution of 8 bits per color, so 24 bits for your RGB, you start to get to some very big numbers. And obviously they're far too big for most FPGAs. Most FPGAs don't have that amount of memory on chip. So you've got to scale back a little bit, both in terms of the color resolution and the number of pixels. Obviously, there are ways to kind of get around that issue. So if you're just using text mode, if you're just using characters, you can offload some of that storage into ROMs. So rather than storing the color state of each pixel, now your frame buffer doesn't have to store each pixel value. It only has to store what character is stored at each character location. That allows us to reduce the size of our frame buffer because we're no longer storing the individual pixel information. We're just storing what characters are stored on the screen. And obviously our characters will have a single color. But I didn't want to take that approach. That was a little bit restrictive. I wanted a purely graphics display, not really interested in having too much text on the screen. So that wasn't really a possibility. So to determine how big the frame buffer could be, obviously looked around at what FPGAs are out there and obviously looking at the lower end of the market, how much memory they had. So looking at the Altera Cyclone family of devices and Xilinx's Spartan 3s and Spartan 6s. As with any FPGA design, typically work with an 80% rule. You can't use all the hardware resources that are available on the chip necessarily owing to routing constraints. So you can see the figures in these tables are indicating the number of bits. So for the Xilinx devices, those are block RAMs. So if you roughly divide by 10, you kind of get into your bytes kind of area. So for your cheap FPGAs, you're looking around about 20 kilobytes worth of internal memory. And obviously some of that has to be used by the processors. Then we have the question of how many bits do I use to represent each color component, the RG and the B. Obviously, typically that will be 8 bits. So that'll give you 16 million colors, which for our simple games controllers is a little bit of overkill. So we can prune that down a bit. So I've decided to go for 2 bits each for the RG and B components. So a 6-bit color code, which obviously gives us 64 unique colors. I think in reality, 16 different colors would be more than adequate. So the character fonts and the tiles were implemented as a 8x8 grid. So using those, I could define my uppercase, lowercase, my alphanumerical characters that would be used as part of the game, but also the tiles used to represent the various graphical elements in the games. So you can see here at the top of the page, we have 2 examples of Space Invader tiles. Obviously for larger graphical elements, that would have to be broken down into these 8x8 tiles to build larger graphical elements. Therefore, I chose a 160 by 120 image size. That gives you 20 characters by 15 characters worth of screen, which seems reasonable for the types of games I was looking at. So to store that pixel data in memory, we will need around about 20 kbytes worth of storage. So we have 160 times 120 times 6 bits worth of storage. But to simplify the reading and writing of that data, we'll be storing that to bytes, so we do lose a couple of bits. I could have used that extra 2 bits to increase the number of bits representing the RG or B component. I also pondered using those 2 bits as some sort of modifier, some sort of status bits for those pixels. But for this first version of the video display controller, I decided to keep things simple, so those extra 2 bits are actually lost. So to store in the FPGA 1 frame's worth of data, I need 19,200 bytes, which is quite a lot of memory. Combined with that, obviously, I need to store my font data and my tile data that I'll be using for my graphics. To store my basic ASCII character data, I need 128 times 8 by 8 pixels worth of storage, so that's 1 kbytes worth of storage. I decided to go the same with the tile memory. So within the video memory, I'm also storing the graphical tile data used in the game. So again, I went for 128 tiles, which is another 1K. Processor memory is 4K, but it's 4K times 16 bits, so that's 8 kbytes worth of storage. So if you add all that up, I get 29,440 bytes worth of storage for our video memory. So I decided to implement that as 16-bit memory. So I'd be storing 2 pixels worth of data in each memory location. The reason for that was I was trying to preempt any memory clock speed issues when dealing with the control logic that would be writing this data to the display. So rather than implementing it as byte memory, implementing it as 16-bit memory meant that you could effectively prefetch pixels so that in one memory transaction you were reading 2 pixels worth of data increasing our memory's bandwidth, and as I say, hopefully reducing the required clock speeds. So here we have our memory map for our video controller. So the first 20K's worth of storage is the frame buffer. Our next 2K is for our fonts and tiles, and there's actually a little bit of space left over for future expansion. So here we have the block diagram of the video display controller. So our video memory is implemented as dual port memory. That allows the display interface controller and the CPU interface controller to operate in parallel. So the display interface controller generating the RGB, horizontal and vertical control signals can be reading the frame buffer, updating the display, and at the same time the processor can be writing the next frame's worth of data to the same frame buffer. Obviously that may have some synchronization issues in that when the processor is writing to this buffer, it doesn't know what part of the screen the display interface controller is updating. So that could cause some issues. I could add some hardware synchronization information to the video display controller such that the processor could read what row or what column it is currently updating. Has it finished updating the display? Has it finished reading the frame buffer? But at the moment that doesn't seem to be an issue. I'm not seeing any artifacts on the display because of this. So at the moment, we're going to stick with it. It seems okay. So the resolution I chose to help minimize the memory requirements is 160 by 120 pixels, but that's a little bit on the small side. So integrated into the display interface controller is an upscaler. So what it will do is it'll upscale that by 4. So every pixel in the frame buffer is repeated 4 times on a row, and then that row is repeated 4 times. So that upscales it to 640 by 480 VGA resolution. That obviously does mean that you have chunky pixels, but for this game it's still in character. I don't need the lower level resolution. And by doing that, that enables us to use cheaper, smaller FPGAs. Another design decision that needed to be made was how much hardware support the video display controller should give to the processor. And if you look back at some of the early 8-bit computers, quite a lot of the graphical functions were implemented directly in hardware. A common technique was to use sprites, so that introduced the idea of a background layer and a foreground layer. So the foreground layer would contain your sprite, comparable to the Space Invader tile I showed previously. However, these were implemented directly in hardware, so it was very easy to move these around the screen, as you could just give a movement command to the hardware. And commonly the hardware would also implement hitboxes, so the processor didn't have to determine if the two sprites were colliding. The hardware could perform those calculations for you automatically, so it offloaded quite a lot of processing into this dedicated hardware. I did think about adding some additional functionalities, but I decided to keep it simple because it simplified the hardware I was designing. So the processor can read and write to the frame buffer, so it can see what the pixel values are set to or set them to a different value. It can also tell the video controller to write a block of color, so defines a rectangular shape. Also, if you've got replicated areas, there's a block copy command, so you could tell the video controller to replicate certain areas of the screen. The draw tile command could be used to draw a Space Invader tile or that had one of the predefined alphanumeric tiles, so you could write text to the screen. Obviously, being 8 by 8 pixels, it was quite chunky text, but that was still useful for games, so you're writing out the score or other game information. In addition to drawing a tile, you could overlay a tile. So the difference there is that if you overlay a tile, black was a translucent color. If you had 2 tiles on top of each other, for example 2 Space Invaders, you wouldn't fully block out the tile you had drawn previously. In the black regions of the foreground tile, you could still see through to the colors of the background tile. They would kind of overlay each other. And finally, you had draw pixels, so that allowed the processor to manipulate a single pixel at a XY position. So in software, I did implement a type of sprite, so you don't have the concept of layers, there's no background and foreground layers, but I did implement a software library that replicated the functionality of a sprite. So you had a software object that defined the sprite's position, its type of movement, and the graphical tile it would use. On top of that, the software library also allows you to draw lines and circles using Bresnam's algorithm. Therefore, using a combination of all these different functions, fingers crossed, touch wood, we should be able to do all the graphical functions we need for our games. One of the other key components that we needed to implement was the games controller. So how does the user interact with our system? So to start off, I used hardware that I already had designed, and that was a serial port. So by connecting a serial port to our processor, we could send ASCII characters from a terminal on a PC to control the game. But obviously that's not too practical. So for the first prototype system, I used a rotary switch, a rotary encoder that was on the Spartan 3 board you can see here. And from one point of view, that was historically correct. The original Atari 2600 used rotary controllers for its games controllers. So for the Pong game, you rotated the control dial to move your player's bat up and down. I believe these original ones were implemented using variable resistors, whereas the rotary controller switch on the FPGA board is a digital encoder. As you can see here, so basically it's two switches giving you a quadrature encoding, so you can determine how far it's moved and what direction it is moving. It also had a third switch. If you actually push down on the control knob, that triggered another button, which I used as the fire button. The hardware needed to interface to that sensor. It was easy to implement because that was already provided by Xilinx as an application note, so that was an easy cut and paste. But I also wanted a fully functional gamepad, a more classical controller. So looking around, the easiest one to interface to the FPGA board was the Super NES one you can see here, because it had a very simple serial protocol. So it's just a synchronous serial protocol. So it was relatively easy to reverse engineer that as a simple VHDL module, which we have here. That was then converted into a graphical element that could be added to our SimpleCPU system. The final interface I haven't got around to yet, supported by this FPGA board, is a PS2 keyboards. So by using a USB to PS2 adapter, I can connect a standard keyboard directly to the FPGA board and then control the game via a keyboard. Or I guess a mouse, so that would also be a possibility. But as I say, I haven't got around to doing that one yet. But again, the PS2 protocol is nice and simple. So fingers crossed, touch wood, that'd be relatively easy to implement in hardware. The final component we need for our games console is that all-important processor, and I decided to stick with the SimpleCPU version 1D. The first prototype system I used to implement the Space Invaders game and the Game of Life, you can see here. A few modifications, so I increased the clock speed to give it a little bit more processing power from 10 MHz up to now 25 MHz. The reason for going to 25 and not higher was because that was the frequency needed by the UART. So to support higher bit rates, the serial port uses a 25 meg clock, so it made sense just to have one clock generator. I think the SimpleCPU logic will go a little bit faster, but if you start to push it beyond 25 meg, you start to have to look more closely at time enclosure issues. In its present state at the moment, I don't have to worry about any time enclosure issues. But going above 25 MHz, you're starting to getting close to your critical path delays. You're starting to get close to your maximum frequencies without giving the software tools some hints about time enclosures. Also, I did add a few more instructions to the instruction set, add a little bit more hardware to the ALU to help support commonly used functionality when writing these games. But no significant architectural changes. It's basically a standard SimpleCPU version 1D. So in this first test system, as you can see here, you have the processor, we have 4K of memory, we have our UART, some GPIO for switches and LEDs mostly, the rotary encoder module, and our VGA controller. So in the final system, we'll have two additional peripheral devices. We will have the PS2 keyboard interface and the Super NES gamepad controller interface. But for the first system, the user interacts with the game via the rotary encoder switch. Debugging information is passed back to the user using the serial port. The current plan is that the processor has a 4K memory space. Within that, I'm allocating 2K of that to system software, so subroutines that will support the various peripheral devices, the video controller, rotary controller, gamepad, etc. And that will leave free 2K for game logic. Now that may sound quite small, but remember that the tile data, the font data, is stored within a block of memory in the video memory, so that frees up quite a lot of space for the processor. And that video memory, again, can be configured by the user and effectively loaded into the bit file that is used to configure the FPGA. So you can add additional tiles and fonts to that video memory for particular games. In addition to that, to help simplify the process of writing games, I've implemented a number of high-level macros that will allow the user to draw graphics, define sprites, update the display, implement game logic, etc. So you don't have to always write the code at the assembly language level. That does come at a little cost, as there's quite a bit of cut and pasting using macros, but it does speed up game development. And I've written a couple of small games now, Noughts and Crosses, a Space Invader-like game, and 2K space for game logic does seem reasonable. The only game where I hit hard memory limits was Conway's Game of Life, and that was mainly down to game state data, because obviously you have to maintain the state of each living organism in that game, so that took up a lot of data memory rather than program memory. So I think for simple games like Pac-Man, Snake, Breakout, Pong, I'm almost definitely confident there'll be enough program memory to implement the game logic for those games. Okay, so that's a not so brief introduction to the SimpleCPU games console. So in the next series of videos, we'll be going through the software. So we'll be looking at the user interface for the VJ controller, the rotary controller, gamepad, and the PS2 keyboard. And the goal here is, once you've got a good understanding of the software library, you can go away and write your own games. Obviously, the hardware is fixed. There's no need to change the hardware. All we need to do is reassemble our program, and we can use the Xilinx command tool, data to memory, to modify the pre-synthesized bit file with a different program. Okay, our journey will continue as soon as I can get around to getting the next video done.